All right, so we're in 4.4, exponential and logarithmic equations preparation. Okay, so the property for solving an exponential equation basically says if you can get the bases to be equivalent, then their exponents must be equivalent. And let me give you an example of that. So let's say we have 9 to the x power. If I did a prime factorization of 9, that would actually be 3 squared. Now, I mean, technically you would just say it's 3 squared to the x, and then 2 times x is 3 to x, because an exponent times an exponent, right? So if you have a power to a power, you multiply them together and you get 2x. Anyways, now if we do a prime factorization of 27, we get a 3 to the third power, right? So what we're really looking at is, since the bases now match, that must mean 2x is equal to 3. So what we end up with is 2x equals 3. Then we undo the multiplication of x by 2 by dividing by 2, and whatever we do to one side, we do to the other. Those cancel out, leaving me x must be equal to 3 halves. Okay, let's try the next one. Now, the first one's already 2 is just 2. That's a prime number, so you don't have to do anything. But 16, the prime factorization of 16 is 2 to the fourth power. So what you end up with is 3x minus 8 must be equal to 4. All right, let's solve this. So we're trying to get the variable term with the x in it, 3x by itself. So we have to undo the subtraction of 8 by adding 8. And whatever we do to one side, we do to the other. We end up with 3x is equal to 12. We undo the multiplication of x by 3 by dividing by 3. Whatever we do to one side, we do to the other. And we end up with x is equal to 4. Awesome. Move on to the next one. Prime factorization of 27 is 3 to the third, so we end up with 3 to the third, and we have to multiply it by the previous exponent, which was x plus 3. That gives me 3 to the 3 times x, which is 3x. So we just distribute this. And then 3 times 3, which is 9. Next, the prime factorization of 9 is 3 to the second power, but then we have to multiply it by x minus 1. So then we end up with 2 times x, which is 2x. We end up with 2 times negative 1, which is negative 2. So now, since they both have the same base, we know 3x plus 9 must be equal to 2x minus 2. All right, I want all the x's on one side, so I subtract 2x from both sides. So we end up with x plus 9 is equal to negative 2. Then we undo the addition of 9 by subtracting 9 from both sides. We end up with negative 2 minus 9, which is negative 11. All right, let's try a couple more examples. Prime factorization of 4 is a 2. Now in this case, you could just say 16 is 4 squared. That would also work. You'd get the same base, right? That's your key, is to get the same base. So you don't always have to do the prime factorization. So for instance, what I mean here is we just keep the first one. And let's say we know that 4 squared is the same as 16. Okay, we could just do this instead. So we would distribute the 2. End up with 3x. 4 to the 3x minus 1 power is equal to 4. 2 times x is 2x. 2 times positive 2 is 4. So what that would mean is 3x minus 1 must be equal to 2x plus 4. All right, so minus 2x, cancel, cancel. We end up with x minus 1 is equal to 4 plus 1 plus 1. And then x must be equal to... Oh, I gave the answer to that one, didn't I? Let's erase that. Getting tired. Plus 1, 4 plus 1 is 5. Okay, so the next one. Next one, to make these kind of look the same, is first I'm going to do the prime factorization of 216, so that's going to be 6 to the third. But it's in the wrong place, it's in the bottom, so I'm going to put it on top, and that's going to flip the exponent sign from a positive 3 to a negative 3. So then what we end up with is 6 to the x is equal to 6 to the negative 3, which means x is equal to negative 3. Okay, so the next problem, we have 2/3 to the x power is equal to 9/4. So 2/3 is factored. So we'll keep that. If I do the prime factorization of 9 over 4, that's going to be something like 3 squared over 2 squared. And then what I can do is I can pull the 2 out of both of them, and that would give me 3 over 2 squared. So that would give me x is equal to 2. All right, let's try the next one. So we have 4 to the x power is equal to 15. So what we can do here is, there's a trick where if you take the natural log of both sides, for instance like that, we could pull this exponent, which is our variable, to the front, and that would give me x natural log of 4 is equal to the natural log of 15. And then to solve for the x, I would divide both sides by natural log of 4 divided by the natural log of 4. Those would cancel out, and your exact answer on this would be your natural log of 15 over your natural log of 4. You can do the same thing with log, base 10 log, and you'd get the exact answer. Now, if you want an approximation, you'd have to plug this into your calculator. All right, so let's try this one over here. Now, let's say we did a log of base 10. It's going to come in handy later on. So we could just take a log of the right side. Okay, so I'd pull the x to the front. So we'd have x log base 10, which, because again the base is 10 and the argument is 10, this would just go to a 1, so we just do it with x is equal to log of 120,000. And that's it.